for this session. It will be Andrei Negut, who will tell us about the PBW basis of the quantum toroidal.
Thank you very much, and thank you all for coming. And please join me in thanking the organizers of this wonderful conference. I think this is a great workshop and a great city. We should do it again sometime. Okay. So let me actually start, because this is the last talk actually in the program. It's kind of funny that I will actually be defining some of the basic objects which have been discussed at least in the previous week, and it's going to be a pretty explicit talk, I guess. So we'll see how it goes. Let's actually start. Yeah, okay. Let's actually start from a very basic definition. So let's start from what whole algebra is. So let's see the category, and we want this to be a hereditary and finitary. I'll define these words in a sec. Abelian category over a finite field, and this finite field will be called F. There will be a Q in this talk, but please mind that the fact that I don't want to put the Q on it because Q will mean something slightly differently. So hereditary here means that the only x which we have between objects, I say abelian, yes, abelian. X I a b is 0 if I is different from 0 and 1, and finitary. Well, everything is over the finite field F, so this is actually equivalent to the fact that the surviving x, namely x0 and x1, are finite dimensional. So, because everything is over a finite field, they are they are sets of finite cardinality. If you have this, you can define a structure which is called the whole algebra of the category. So the whole algebra of C, by definition, I want it over complex numbers. Let's do it over complex numbers. It has a vector space. It's a C vector space with a basis given by isomorphism classes of objects in the category. So A in double brackets goes over the isomorphism classes of objects in the category C. Category C. So this is what it is as a vector space, but I said I want to make it into an algebra. So let's give it an associative multiplication. This will be given to us by the whole product. So I have to tell you how to multiply two such objects. This multiplication is given by the following expression. So if you take an isomorphism class A and you multiply it with an isomorphism class B, you have put here a constant for what I'm about to say soon. But after you put that constant that I'll write down in a second, it's essentially a sum over all other isomorphism classes. So this X in the category C. Well, the class X. And essentially what I'm saying here, we need to put the structure constants in the algebra. The structure constants, they count extensions between A and B, which are isomorphic to X more or less. So in the numerator, you put the number of short exact sequences in your category, which look like this. And in the bottom, you divide by the number of automorphisms of A times the number of automorphisms of B. And I was saying you have to put a constant here if you really want to be completely precise. Over here, you put the cardinality of the home set from A and B, and you divide by the cardinality of the X1 set. Everything is a finite set, so everything over here is 1. Okay, so this is the definition of the whole algebra in general, and I'm just going to briefly write what probably is the most classical example. So what probably is the most classical example of a whole algebra is the fact that the whole...
Sorry, why you need the first condition? Higher x to vanish.
Well, because I'm only invoking short exact sequences. And, I don't know,
You want it to be the Euler characteristic, basically.
Yeah, and they should be like here.
There must be characteristic here, I understand. No, I mean, sorry. The first condition at the top, higher axis vanish. Why you need this condition?
I mean, ultimately, and I'm not going to invoke all of this structure, but ultimately, this is going to be a bialgebra with the co-product and everything, and you want all of these structures to be compatible with each other, so probably need this. I mean, this notion can be defined slightly more generally, but just to keep things simple, we can keep it at that.
Sorry for stupid question. What kind of letter is that?
This is I'll see. It's good. So the classical example over here is that the whole algebra of the category of representation over our finite field of a quiver of finite type. So this is a quiver of finite type. This thing is due to Ringel and Green. This thing is isomorphic to the positive half of the quantum group of type Q, and for the parameter little q over here, you have to put, if I remember correctly, the square root of the cardinality of the finite field. So this is like the classical example, but I will not be talking about this example in this talk. What I will be talking about is something that is also an extremely important example, but it's going to be just a little bit more complicated than this. So instead of working with the category of representations over a quiver, let's talk about the category of coherent sheaves over curves. The first example of a category of coherent sheaves over curves is P1. So let's take C to be coherent sheaves over P1 over a finite field. So if you have this category, let's start analyzing the isomorphism classes of objects in this category, and let's try and compute the whole product over here. I'm not going to actually do this exercise, I'm just going to say what the answer is. So basically, I will make a little simplification. So instead of studying the entire whole algebra of this category, I will study something which is almost as big as the entire whole algebra. It's called the spherical whole algebra. Actually, I looked at Olivier Schiffmann's lecture notes on whole algebras, which have all of these things very well explained, because I really wanted to understand why do we call this subalgebra spherical. And he actually has a footnote in his lecture notes saying that he doesn't know.
No, I mean, because of theory of automorphic forms. So they have spherical functions.
So maybe the lecture.
Harmonic analysis.
Harmonic analysis.
Okay, all right.
Real group.
But they defined already something which is spherical. You are right, because this commutes with T. Okay.
All right. So that my joke was annihilated. What is this in this example? In this example, this is the direct sum of the isomorphism classes of vector bundles. So instead of studying all coherent sheaves, I'm saying let's just look at vector bundles. It's not a really big difference on P1 because a coherent sheaf on P1 is a vector bundle plus a torsion sheaf, but let's just study vector bundles. Because of the theorem that any vector bundle on P1 is isomorphic to a direct sum of the line bundles rho of I, then it follows. From this, you can show, because it follows that the spherical whole algebra is generated by the classes of these line bundles. Has an algebra. So then you can ask, well, we have a set of generators for this algebra. Can we work out a set of relations in this algebra? And answer is given completely in the following theorem of Caprano, who tells us that there exists an algebra isomorphism from UQ up, not Q, square root of the cardinality of F. Yeah, I think it's just not this inverse. Anyway, U something SL2 hat. I defined his quantum group in a second, and SH, the spherical whole algebra of the category, and this isomorphism is given by sending the generator called EK to the class of the line bundle of Q. So then I just have to tell you what this object is. So this object is the positive half of the affine quantum group of type SL2, the easiest affine quantum group you can have. So this thing is generated by the EKs, as I promised you. But I have to tell you what the relations are. So this is generated by EKs as K goes over all the integers, which kind of makes sense because if you want these line bundles for all integers K, modulo the following relation. So this relation is going to be of the kind we're going to see repeatedly in this talk, so that's why we're going to write it explicitly. EZ-EW, Z times the cardinality of F minus W is equal to W EZ, Z minus W cardinality of F, where E of Z is just the bi-infinite power series that is obtained by connecting all of these generators together. So E of Z is just a generating series kind of way to collect all of these EKs together. So how do we interpret these relations over here? Well, you just extract the coefficient of Z to the power m, W to the power n for all integers eminent from this formula, and you will get an infinite family of quadratic expressions in the EKs, which are the defining relations in the positive half of this quantum. So what Kapranov is telling us is that in the spherical whole algebra of this category, a complete set of relations, of multiplicative relations among these line bundles is given by these quadratic relations over here. Pretty much everything is happening in degree 2, which is a very nice example. So this has been the first...
We just mentioned this is his paper about Eisenstein series.
Yes. Probably if I would have looked at that paper, I would have known the answer to...
So there's another story which is elliptic hole, but this is...
well, elliptic hole is going to come now. So,
yes,
so elliptic hole means the version of this construction when P1 is replaced by an elliptic curve. Right? So let me talk about elliptic hole algebra. The elliptic hole algebra is the next case, the case when instead of the category Coh P1 over F, you take the category C sub 1. Co1 here, by the way, it doesn't mean a genus. You're going to see what it means at the end of this talk. So it's the category of coherent sheaves over an elliptic curve over a finite field. Now, there are quite a number of elliptic curves over a finite field. So to describe this elliptic curve, let me assign some values to the Frobenius eigenvalues of it. I'm going to do something a little bit weird. I'm going to ask that the Frobenius eigenvalues of E be denoted by some weird symbols, which may not seem logical or reasonable at first, but they will be reasonable toward the end of this talk. So the Frobenius eigenvalues will be called Q squared and Q plus squared. Right? Why not? If you do this, then the number of the cardinality of the finite field is going to be the product of the two eigenvalues, which I denote by Q minus to the minus 2.
Footnote size is good in papers, but not on the blackboard.
Oh, sorry about that.
No, it's okay, it's here. Frobenius eigenvalues.
All right.
If you do it just once, it's fine.
Just once, I will. it's too high for me. Anyway, so a number of points in this finite field will be denoted by Q minus to the minus 2, where Q minus is the inverse of the product of these things. So where Q plus Q minus is equal to 1 over Q. So let me circle this because we will see these parameters appear over and over again. So yeah, it's kind of a weird asymmetric choice of these things, which will pay off at the end of this talk when I will discuss a mysterious category to be called Cn. But for the time being, this is just an odd choice. Okay, what can we say about the category of coherent sheaves on an elliptic curve? Well, here are a couple of basic facts. So any object A inside here has a degree and rank. So to A to an object A. In here, we can associate what I'm going to call A bar, and this is just the pair between the rank of A and the degree of A, which is an element in n times z. Strictly speaking, because you could have a torsion sheaf, you should put n0 here, but we will not be worrying about torsion sheaves too much in this talk. So this is, in a sense, a numerical invariance of A. Also, very important, the slope of A is going to be defined as the slope of this lattice point, namely the degree of A divided by the rank of A. Now, if you have these two notions on a curve, you can define the notion of a semi-stable coherent sheaf. So I'll tell you what it is. A is called semi-stable. I mean, you can say semi-stable of slope mu if you want. No, A is called semi-stable if any subsheaf of A has a smaller slope, not necessarily strictly smaller, but smaller slope. It's a pretty standard notion. The reason why we care about this is because if you have a notion of semi-stability, you have a notion of the Hardern-Harasim-Hanfi filtration, which is saying that you can actually build an arbitrary object in this category from the semi-stables. So, strictly speaking, what this is saying is that any object of the category, any A inside the category C1, has a unique filtration, whose successive quotients are semi-stable. Quotients are semi-stable and have slopes that form a decreasing sequence. Stable and have decreasing slopes. Now, the question of filtrations with successive quotients being semi-stables actually fits in wonderfully with the definition of the product in the whole algebra, because over here you're interested in short exact sequences. It's going to turn out that if you know that A and B are semi-stables and their slopes are ordered in just the right way, then such short exact sequences are actually in one-to-one correspondence with objects in your category. So what you will get out of that as a corollary, it's not quite an immediate corollary, but it's almost, you will get the fact that the whole algebra of the category C1 actually is a tensor product, at least as a vector space. It's a tensor product of the whole algebras of the categories, the subcategories of semi-stable. So this tensor product is taken over all rational slopes, including infinity, strictly speaking. The tensor product here is an increasing order of mu. And C1 mu, I'm going to write here because I know it's illegal to write under this line. This is the subcategory of semi-stable coherent sheaves of slope mu. Semi-stable slope mu. So in this way, you get a decomposition of the whole algebra. So instead of trying to understand this big thing, you might as well try to understand the building blocks for each individual mu, and then you have to understand how they fit together. Unfortunately, even the task of understanding the building blocks over here is pretty hard. So, in just a couple of words, we were able to get, or Kapranov was able to get this nice theoretic presentation here because, in a certain sense, the number of generators, or the generators of this whole algebra, did not really depend on the curve, because there's essentially a single P1. But there are a number of elliptic curves, and that means that you do not have a uniform way to parameterize the generators in the whole algebra of this category. There is no uniform way to parameterize even line bundles on her elliptic curves, because the number of line bundles depends on the number of points on your elliptic curve, and this does not just depend on the cardinality of f. It's a set of generators which you cannot easily control. So because of that, there is little hope to get a complete representation theoretic understanding of this whole thing. So what Burban and Schiffmann say is, let's instead study a slightly smaller or a somewhat smaller subalgebra. So they say the following. Let us consider the following subalgebras of the whole algebra. So instead of considering the whole thing, consider the subalgebras SH C1 mu. So these are subalgebras of the individual pieces over here. So this is SH. This is going to be denoted by SH C1 mu. I guess this is my notation. We'll see why I call it SH in a bit. So this is defined as the subalgebra generated. What field was I working over C? Let's do C. This is the subalgebra generated by the following symbols. They are called E-A-K, E2A2K, dot, 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 where? And let me tell you what these E-A-Ks are. I'll tell you what A and K are. So A and K, K divided by A is a reduced expression of a slope mu. And now I have to tell you exactly what these E's mean. The definition of E SASK for any natural number S is the following. So I'm going to put here an overall constant, which is Q minus the ds, and then I'm just going to sum over all isomorphism classes of objects which are semi-stable and have numerical K-theory class equal to SAS. And I'm going to put here the class of the object. So what's going on here? Instead of studying the individual isomorphism classes of objects in this category, or the individual isomorphism classes of semi-stables in this category, they are saying, let us consider instead this average where we literally sum over all isomorphism classes of semi-stables with the chosen numerics. And you do this for any choice of numerics over here. If you do that, then you can say define SH of C1 as the subalgebra of HC1 generated by these subalgebras over here. E SASK. So I really should say exactly what parameterizes this. So A is a natural number, K is an integer, the GCD of A and K is 1, and S is an arbitrary natural number. So this is the parameterization of this. So at least now we have a definition of what is the whole algebra we want to consider. It's a particular subalgebra of the whole algebra of this category, which is generated by certain averages of semi-stable coherent sheaves. And the next step, which I will show you on this board over here, is how to get a description of the spherical whole algebra, which is analogous in a certain sense with Kapranov's result, meaning how to get an explicit generators and relations presentation of the spherical whole algebra of this category. But before I do that, I do need to slightly change notation, and instead of working with these E's, I'm going to present all the formulas in terms of a related system of generators, which are known as the P's. And the P's are related to the E's by the following formula. So this is equal to 1 to infinity okay, is equal to exponential ESA SK divided by S. And you you can imagine, I mean, this is a connection between complete symmetric functions and power sum functions, but I'm going to allow myself a freedom of multiplying by a certain constant here, and the constant I'm going to multiply is this thing times this thing. So it's a funny looking constant, and it's a choice of normalization which is going to work for me. And if you know the original definition of these things from the paper of Burban-Schiffmann, you will notice that my conventions over here are not exactly standard, but you will see. I hope it will pay off quite soon. So the p's are related to the e's by the formula over here, and I'm going to define some other generators here which I call e bars by essentially the same formula, but I will flip the sign of the p's and change the constant just a little bit. So this is minus, and you have the same sum over here. And I promised you I would be flipping, I would change the constant, so I'm going to put x divided by q inverse and the same qx minus q minus. Alright, so we have a set of generators of this algebra called e's, and instead of presenting things in terms of e's, we could alternatively write them in terms of p's and e bars. And all of these actually will appear in the relations that I will write in a second. Any questions on the geometric nature of this whole algebra? Because what's going to happen now is going to be a lot of combinatorics. Okay.
Just to clarify, letter P appears, right? You will use it later here.
Letter P. Oh yeah, I will use it in the theorem that I will write on this board.
So the relations will be given in terms of P's, not in
well,
terms
the relations will be. You will be interested in relations between the p's, but the right hand sides of the relations will involve e's and e bars. So that's why I'm defining them in this way. So here's the theorem, and this is due to Burban-Schiffmann. And they say the following thing. It's gonna be a long statement, so please bear with me. Let A sub 1, I guess, because anything until now has been sub 1. Let A be the algebra. Let's do Q of Q plus Q minus algebra generated by symbols P, S, A, S, K. I mean, I'm just going to say by P, A, K with A in the natural numbers and K in the integers, modulo the following types of relations. So there are going to be three relations here. Relation 1 is saying that A1 mu, which is going to take the form k over a, which by definition is the polynomial ring in the symbols p(a)k, p(2a), 2k, dot 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 inside A1 is an algebra homomorphism. So this is just a clunky way of saying that symbols PAK, P2A, 2K, P3, 3K, and so on commute. But you'll see why I'm writing this when we write the generalization of this algebra. So statement number 1 is saying that the algebra A1 actually has a family of subalgebras which are indexed by a rational slope, and all of these subalgebras are just polynomial rings in infinitely many variables, so they are quite simple commutative algebra. Relations 2 and 3, which I will write now, have to do with the interaction of PAK and PA prime K prime for different slopes, and they will be a little bit more tricky. So here's relation 1. It's saying that the commutator of PAK with PA prime K prime, this thing is equal to the following logic: PA plus A prime K plus K prime times a constant, which I will write for you in a second. But I have to tell you what the restrictions on AK and A prime K prime are. This relation will not hold for all lattice points here and lattice points here. This holds if the number D, which is defined as the determinant of this matrix, is satisfies absolute value of D is equal to GCD of A prime K prime. And I told you that there's a constant here. We'll tell you what this constant is. This constant is Q plus to the D minus Q plus to the minus. Anyway, if you're okay with constants, then essentially the commutator of these two generators is equal to, well, the generator when the indices is the sum of the lattice points in question, but this only holds if the property over here takes
Do you mean square of it or something? D square? Because if they're both proportional.
What's that?
If you scale both of the vectors by 2, so the determinant will multiply by 4.
Yes. But you're not allowed to have that. So if you scale these two vectors by 2, you will not have this relation anymore. So this relation, in particular, it requires the vector AK, the lattice point AK, to be primitive. If AK, if the GCD of A and K is not 1, then you cannot have this. And actually, I was gonna do this later, but the lattice point interpretation of property 2, let me write it here, is the following. So this is a vector A comma K, and there are no lattice points on this vector except for the tail of the arrow and the tip of the arrow, and then you have the vector A prime comma K prime, which I will draw here. You may have lattice points over here. You are allowed to have lattice points over here. But what the theorem is saying is that there are no lattice points inside this triangle. So to be in the situation of 2, you must not have any lattice points inside this triangle, or on this side, or on this side. But you may have lattice points on the side. So that's property 2. Property 3, which I will write in a second, is exactly the situation of this lattice triangle, when instead of having a lattice points allowable on this edge, you have the lattice points allowable on the bottom edge. So this is the situation allowed in 3. And this vector over here is going to be the sum of the two vectors, and you allow yourself to have lattice points on the hypotenuse of this triangle. So what does property 3 actually say? Well, it says that the commutator of this thing, PAK with PA prime K prime, is equal to, and let me try and remember this. So this is going to be sum over all S plus T is equal to A plus A prime. And I'm going to put here an E bar and an E, and the indices I'm going to have to put are S comma mu S. I'll tell you what mu is in a second. E times T mu T, and here I'm going to have to multiply everything by a constant, and this constant is this thing here. Anyway, so you can neglect a constant if you want. It's going to be important in a bit. The moral is that in the right hand side of this relation you have some kind of high linear form in the E's and E bars. So this happens if I'm running out of space.
Well, use this part.
No, because I want to keep this. So let's write.
Are you seriously going to use these formulas?
Oh yeah.
Don't decide it.
So if the determinant, let's write this. If the determinant of Ka K prime A prime is equal to the GCD of A plus A prime K plus K prime, and the only other thing I need to tell you to make this this formula complete is what mu is, and as you can imagine, mu means the slope of the hypotenuse in quotes. So let me actually write it here. So mu is equal to, and this I will use, mu is equal to K plus K prime divided by A plus A prime. And it's essentially the slope of this line. Okay, one more condition over here. So in order for these things to be well-defined elements in the algebra, S and T should be natural numbers, and mu S and mu T should also be integers. So in this condition, to make everything completely correct, I need this condition over here. So this is the elliptic whole algebra that you heard some. Now I wouldn't necessarily say so much about in this workshop, but something about in this workshop. And this is a very non-economical and bad way of writing relations in the elliptic whole algebra, because with a little bit of thought, you can actually find a way to take relation 2 and relation 3 and package them into a single type of formula. That's actually how Burban and Schiffmann actually first wrote these things down. Also, relations 2 and 3 actually have a non-empty intersection when a triangle over here has no lattice points on any of the edges, in which case, it's an exercise to show that the right-hand side of this thing is equal to the right-hand side of this thing, despite the fact that this one is presented in terms of p's and this one is presented in terms of p's and e1s. But when all this is said and done, what this actually means is, what's going on with this algebra? Well, it has generators which are indexed by lattice points, and in the notation over here, these lattice points are contained in the right half plane. And the relations between these lattice points have to do with the commutators of these p's when the corresponding lattice points are close enough. So the emptiness of this triangle or the emptiness of this triangle is a way to measure that the vector ak and the vector a prime k prime are close enough. And geometrically, what these relations mean is that if you take an extension between hemistables of two slopes in the wrong way from the point of view of Harder and Narasimhan, then you can describe the corresponding set of extensions in the right way by having this what's the word I'm looking for? Well, by having this generator over here and the generator over here in the right hand side. So that's what these relations mean to me.
Sorry, so this algebra is isomorphic to SH, and this is the theorem.
Oh, yeah, well, that's actually, I haven't written down the actual theorem, I apologize. I have to write for you the actual theorem over here. No, over there, so it's just a definition. Let me write down the main theorem on this board.
And when you don't have those conditions satisfied, there's no relation?
What's that?
When you don't have those conditions satisfied with AK and A prime K,
there's
no relation.
No relation, but it's actually shown, I think, maybe even in the original paper of Burban and Schiffmann, that you can describe the commutator of any two elements in this algebra by something in the ideal generated by these relations. It's just that if you take arbitrary AK and A prime K prime, the right hand side will not be explicit. It will be implicit in terms of what follows from these relations. So, in a certain sense, I would say that Burban and Schiffmann show that those types of relations over there are the minimal set of relations who describe all commutators in this algebra. All right, so let me make a couple of remarks. Actually, let me complete a theorem first, because I still owe you a statement. So what they show is that there exists an isomorphism between the spherical whole algebra which they considered and the specialization of this algebra A1 when her parameters Q and Q plus are specialized to the Frobenius eigenvalues of E's, as I mentioned before. So when Q and Q plus are the Frobenius eigenvalues of E. Also, it's not immediately obvious from the relations over there, but it's related to the answer I gave harmonic expression that products of these PMNs form an additive basis of SH of C1. So products of P, K, SA, S, K in increasing order of the slope these things form a basis, an additive basis of the spherical whole algebra, or I guess of A1. And because of that, I will refer to this as a PBW basis, and this actually has to do with the title of this talk. All right, that was theorem 1 actually. So this is the main theorem, I would say, which I wanted to show you, and it's actually the one I am unable to generalize. The one which I will show you how to generalize is theorem 2, which is something that was proved by Schiffmann, I guess, a couple of years after this result. So it was really good that we have this this algebra A1, but we have to relate it with existing algebras in representation theory. And it actually turns out that it's related with a lot of things that we have seen in his workshop. So it's related to the spherical Taha of type A infinity. It's related with some doubly deformed algebras which arise in conformal field theory. But what Olivier proved is that it's actually closely related to something which looks a lot like UQ of SL2 had appeared in Capran-Hobbs result. So what Olivier showed is that there exists a algebra isomorphism between this algebra A1 and something which I'm going to call UQ plus Q minus of GL1 hat hat. So this object over here is called the quantum toroidal algebra of type GL1 hat hat. If GL1 hat were a Cosmos PBW algebra, this would be the quantum affinization of that. It's not quite. So I will give you an ad hoc definition of what this object is. This is the algebra generated by symbols EK over all integers k, modulo the following relations. So if you recall how the relations in SL2 have looked like, you had some biinfinites series being equal to each other, and then you had some linear factors. The same thing holds over here. It's just that the linear factors become a bit more complicated. So the relations take this form: z minus q squared w, z minus plus square w, and z minus q minus square w. This is equal to minus the expression where you switch w and z. So if instead of having these three factors over here, you just had one of them, you would get exactly the defined relation in SL2 hat, which we saw at the beginning of this talk. But this is what you have in this case. And this is actually not enough to describe the relations in this algebra. You also have a cubic hair-like relation. So I'm not going to say what it is, but I'm going to say that it's a hair-like relation. What is the snapshot of all of this? Well, combining theorems 1 and 2, you have an analog, or I guess an analog. Combining theorems 1 and 2, we get an isomorphism between SHC1 and UQ plus Q minus of GL1 hat hat. And this is an analog of Capran-Hobbs result for an elliptic curve.
So that's an EK, that's the P1K.
Exactly. I forgot to say it, right? I will write it in a second. So indeed, the isomorphism over here sends EK to P1K. It's actually not very... That something like this holds is not too surprising, because it actually turns out the algebra A1 is generated by the P1Ks. And you can actually see it from, say, relation 2 over here. So if A is equal to A prime is equal to 1, you can get P2 blah as a commutator of P1 blah. And then so on and so forth. Iterating this kind of argument, you can show that the algebra A1 is actually generated by these P1Ks. let me make a couple of remarks about this. So, what does this have to do with other things in topology and in representation theory? So, just in representation theory, let's call this isomorphism here phi, and let's say that phi inverse of PAK give a PBW basis of the quantum toroidal algebra, which is something that you don't have by other means. Basis of U plus Q minus of GL1 hat. So there's a general philosophy on how we get PBW basis in quantum groups of finite and affine type, but they don't work in the toroidal case, this double affine case. You have to construct these kind of bases in a certain sense by hand, and by the isomorphism with the elliptic rule algebra is one way that you can get this PBW basis. And actually, I think it's the most straightforward way as soon as you have Olivier as a result here. Yes?
There is sort of similar geometric interpretation for the Cartan and UQ.
Yeah, so the half of the Cartan of U of Q would correspond to torsion sheaves in the whole algebra. Not quite to all torsion sheaves, but to averages of torsion sheaves over all the closed points on the elliptic curve. And then everything I'm saying in this talk can be doubled, so you can have, just like you have a double of this algebra over here, you can have a double of the algebra A1 just by taking generators P, A, K, where A and K are arbitrary integers, instead of requiring that A be a natural number. And the commutation relations actually look a lot like what we have over there, but they are a little bit more complicated to write down.
Can you make elliptic curve singular?
That will be related with what's going to happen in 5 minutes. But I still have a couple of remarks here. So, because the workshop is called Low-Dimensional Topology and Geometric Representation Theory, let me say a couple of ways in which this elliptic whole algebra connects with other things that we have seen. So, these things, phi inverse of P of AK, they yield Hovanov homology for torus naught, for the AK torus naught in this case. So this was observed by me and Eugene Gorsky a number of years ago, and it was proved as a consequence of the work of Elias and Hogenkamp and then of Melit, who generalized it for all the NKs. Also, in terms of topological interpretations, Samuelson and Morton proved that if you take this algebra A1 and you specialize the parameters, I guess in my notation you would specialize Q minus is equal to 1, this thing is actually isomorphic to the skein algebra of a torus. So this is the skein algebra of S1 times S1, which kind of explains what the topological interpretation of this first bullet over here is. And as far as I understand from people in this audience, there is a lot of work by a number of people in this audience to find topological interpretations of A1 in the absence of this restriction, and it would be wonderful to see this thing completely developed, but I don't have anything to say about that. So it's elliptic whole algebra, even though it's a purely computational thing, it's actually connected with a lot of things in representation theory and in algebraic geometry, because these whole algebras ultimately are whole algebras of categories of curves. So in the remaining 10 minutes, my goal is to generalize this in the following sense. So the ultimate goal of this project, which I don't have yet, is to generalize this whole thing from GL1 hat hat to GLN hat hat. So the goal would be to find a category Cn whose spherical whole algebra has a property, well, spherical would be defined in a certain way that would only be apparent after you define Cn itself. But the point is that the spherical whole algebra of this category should be isomorphic not to GL1 hat hat, but to GLN hat hat. So I have to tell you what UQ of GLN hat hat is. So we still have two parameters, Q plus and Q minus. So what is this algebra over here? Well, this algebra is generated, instead of being generated by a single family of EKs, as we have in the case of GL1 hat, it's generated by n families of these. So generated by these things when I goes over z mod nz and k goes over the integers. And now I have to give you relations. Here's how they look like. So the relations take the following form. EI of z, EI of w times z divided by q minus wq. This thing is equal to the opposite, EW EZ. I don't think we need this anymore. And here you put ZQ minus W divided by Q. And then, these are all I's. These are all I's. I also have to tell you what happens if you put I plus minus 1 over here and EI over here. And you're still gonna get some kind of commutation relation, as you would expect. But the constants over here, the Q's, are gonna be just a little bit different. The Q's you put here are exactly Q plus and Q minus. So this is one reason why I chose the parameterization of these constants as Q plus and Q minus, because it allows me to easily write down these relations over here. Anyway, the precise formula is maybe not super important over here, but the catch is that the expressions are still quadratic, and they involve some linear factors over here, and then EI of z and EJ of w commute if j is not equal to I or I plus or minus 1. So this is if j is not equal to I plus minus 1. And also, before we have a cubic hair-like relation, which I'm not going to write down. So the problem.
Andrei, frankly, do you really believe that it's some kind of whole algebra? Do you have some suggestions? What can it be? Definitely not the genus 2. What can it be?
That would answer Alexei's question. So I am not the person who to ask about this. I asked this question to Olivier a couple of weeks ago, and he has a number of candidates for what could be the category whose whole algebra is this thing. We cannot prove that any of those candidates are actually have the right whole algebra, but it should have something to do with some kind of singular elliptic curve. The problem is, if you have a singular elliptic curve, it's not going to be clear which category of coherent sheaves you should take on that singular elliptic curve. Because you really want something that will be exactly of the same size as GLN hat, and nobody can prove exactly what the right choice is.
But this is the degeneration of the old construction. How degeneration of the old construction can produce some inequality?
Well, I mean, it has to be something where the simple generators, instead of being parameterized by a single integer, can be parameterized by n choices of integers. So it's not exactly a degeneration of that thing, I would say.
So why I would have thought from that you would talk about this kind of flag varieties that you.
Oh no, I don't think it has anything to do with flag varieties. No, I don't think it has anything to do with that. You just have to find a suitable replacement for a smooth elliptic curve, and a suitable motion of the of a category of coherent sheaves on that thing, whose whole algebra has exactly the size you want, and as much as this GLN has.
Okay, so recently there is a theory for arbitrary plane curves of groups, any genus,
yes.
Right? But this is just local. Do you mean some global?
No. I mean, there's a version of all of this when you have a smooth curve of genus G, and this has worked out by Schiffmann, Hasro, and Kapranov, but they don't have an isomorphism of that whole algebra with anything as easy to describe as GL1 hat or GLN hat. So in the cases of higher genus, it's not really well known how to describe these.
But this I mean something special with my recent results with Phillips. You know, any plane curve singularities, compactified hypothesis in any ranks.
I mean, how do you say
this
that?
Is local. If you
these
mean
whole
global,
algebras are global objects.
This is local story, right?
These whole algebras are global objects.
Huh? You need global.
Yeah,
That's what I
think
want to expect
so
from you,
it's
right?
not going to be.
It must be global.
Yeah, exactly.
Very naive question. What can we mean in terms of circularity?
Well, so
You're not
yes.
changing flow, you're just changing sort of some.
So to be honest, I'm not really sure what the right choice would be. To be honest, so I mean, I think it's better that I don't make statements which I would regret later. Especially since most of the ideas of the geometry of this thing come
You can
from Olivier.
speculate, we can keep secret.
I posted on the internet.
Okay, you're easily optimistic, right?
Oh yeah, I mean, if I weren't, I wouldn't be giving this talk, right? All right, so any yes.
So this is a speculation question. I'm going to ask it anyway. You can answer it. So when n is 1, you have like this nice action on symmetric function.
Yes.
Right? Like nabla.
You would want some actions of the n thing. Well, I do not know what this mysterious category over here should act on. But so how I like to say exactly what I can do here. So essentially, what I want to show you in the last 5 minutes is an analog of theorem 2. So now let me show you an analog of theorem 2. In this case, analog of theorem 2. So i.e., I will build an algebra called an algebra an, which will be isomorphic to u cubed plus q minus of gln hat hat. And this algebra, by its very construction, will have an explicit PBW basis. So as a consequence of this, from the point of view of representation theory, I'm constructing a PBW basis of this quantum toroidal, which as far as I know was something I've before known in representation theory. But from the point of view of whole algebras, what the basis of this algebra will tell us will be some kind of combinatorics on what to expect from the indecomposables in this mystery category. So it's going to give us some information on how the extensions between indecomposables in the category Cn should behave, and this hopefully will help us guess what the right category Cn would be. So, in the last few minutes of this talk, I'm just gonna tell you what the answer is. Yes.
You forgot the plus in your.
What's that?
You forgot the plus.
U plus.
Oh yes, has plus. So everything is done for plus, even though it can be doubled. That's not going to be a problem. So if I tell you what the algebra is, let me recall for you in 2 minutes what can we say about gln hat, gln with a single hat. So gln with a single hat, or in this case uq of gln with a single hat, it has, as far as I know, I mean, it has 4 presentations, but I would be concerned with two presentations of this object. On one hand, this thing is isomorphic to uq of sln hat, tensor product uq of gl1 hat. And since everything is plus, the object over here is just a commutative algebra in infinitely many variables, and this object over here is just a quantum group which we know and love. Because of this, you can.
It is not Heisenberg. It is there's no sense.
It is a positive half of Heisenberg, which is just a
positive
commutative algebra in infinitely many variables with infinitely many generators. Because you have this isomorphism here, you can actually write down explicit generators of uq/gln hat. So this thing has generators which I will call ei, and I goes over z mod nz. And this thing over here has generators which I will call PL, where the L goes over the natural numbers. So this is presentation 1 of this quantum group. Presentation 2 of this quantum group, which is equivalent to it, even though this is not explicit, is that this thing has generators which will be called EIJ, and IJ over here are indexed by a pair of integers modulo simultaneous translation by n comma n, and if you think about it a little bit, these are exactly the positive roots of the algebra of type k n hat. So they are indexed exactly by pairs of integers, one smaller than the other, up to simultaneous translation by n. Alright, so this is what we know about UQ GLN hat. What can we say about GLN hat hat? So let me just write it extremely quickly. So by analogy with what we have over there, we say let AN be the following algebra. Well, I'm going to write it for you as a vector space. So as a vector space, it's going to be tensor product over all rational numbers of subalgebras A and mu. So now I have to tell you what A and mu is. So if the rational number is written as k over A, this thing is defined as UQ GLN hat. So with a single hat over here, but you don't take n, you take n divided by g, and you take g copies of this, where g is the GCD of n comma a. And a is the denominator over here. So what's happening in the setup is that, as opposed from the case over here where everything was all the slopes subalgebras were the same thing, over here you actually have the slope subalgebras will depend on the number g, which depends on the number a. Alright, these things are particular instances of the quantum groups over here, so I can index their generators, and I will index their generators in the following way. It has two types of generators. These will be called Pij, and here I'm going to put a number k, and it's going to have these generators if k divided by j minus I is mu. So these will be analogs of the E generators, of the EI generators, and then we will also need generators PL delta comma R k if this is just a notation here and delta. I can elaborate on it if I'm out of time. So this is if k divided by NL is equal to. So these are generators in this algebra, and now I have to tell you relations. Modular relations. Well, relation 1 is just as before. It's saying that AN mu inside AN is an algebra homomorphisms. So it's saying that the slopes subalgebras are not as vector spaces, but they actually are subalgebras. And then you have analogs of relations 2 and 3. The combinatorics is going to be similar with what's happening over there. So relation 2 says this thing. Relation 2 is a property of what happens. You take a commutator of an element of this type with an element of this type, and here you put this thing. I'll just do one more second. Here you put k plus k prime, and here you put q plus to some d minus q minus to some d. Q plus to the minus d, and there's some constants here which I don't have time for. And then relation 3 is an analog of relation 3 over there, and it's saying something about the commutator of Pijk with Pi prime j prime k prime. So you have a q commutator over here. There will be a certain power of q, and in the right hand side you have a sum over certain s and t's, precisely of e's, which will take the following form: Pj r e is bar EIS times a certain constant, which will parallel the constant of it. So I don't want to take any more of your time. I apologize for going over. I just want to point out the fact that in the right hand side of this relation you have E generators, which are generators of this form, and in the left hand side you have P generators, which are generators of this form. So you can't really formulate the defining relations in this algebra except by taking into account both types of generators of UQGLN hats. So that's why the N case is a little bit more complicated than the 1 case, and you need more notation just to set it up. So thank you very much, and I apologize for going over.
second presentation was like a shuffle algebra type presentation.
No, none of them is actually. That's a different presentation of these algebras which I did not have time to even introduce.
But do you have like shuffle kind of expectation here?
So UQGL1 hat and UQGLN hat both have shuffle algebra presentations, and that's what I used to prove the main theorem, which I actually kind of realized I didn't even say what a theorem is. That the theorem is that the algebra AN over here is isomorphic to UQGLN hat. So to actually prove that theorem, you need the shuffle algebra interpretation, which I didn't have time to say anything about in this talk.
Just to clarify, what you mean by singular elliptic of genus greater than arithmetic genus greater?
No, I think.
Or just cusp? Cusp
it
or,
should probably have some kind of singularities.
So still, genus will go up, right? Arithmetic genus will go up.
No, the geometric genus, I'm sorry, yeah.
Yes,
So that's,
but it is adding singularities on top of elliptic curve, right?
yeah, pretty much.
So these slopes of algebras are different?
Yeah, they change with the slope. So some of them will be GLN hats, and some of them will be GL1 hat plus times GL1 hat times GL1 hat, dot. And some of them will be in between.
Any further questions? If not,
Thank you.
Finally, I wanted to first of all apologize on all the organizers besides Peter for not being here when you thanked us. And I really wanted to thank everybody, so the speakers, especially the plenary speakers last week, and all the people who gave supplementary lectures. I hope that the students found things more useful because of it. Also, all the students who are taking notes and who are running the cameras, so especially Alex and Patrick, who did extra sessions of all that. Most of all, they've left already, but can we still please, I'll show them the video, can we give a round of applause to the ICMS people who are just awesome.
Since they missed it before, we should thank the organizers.